Hello, everyone, and welcome back to a new episode of Advent of Code. So, if you're watching this, you may be surprised because we already did day 13. That was, I'm uploading these a little bit out of order because I did episode 13 as a live stream, and I had to do that before I had time to record number 12. So this is one of those episodes where I've already done the problem, and I'm just going to walk you through my solution. But let's start by reading the problem. Day 12, Digital Plumber. Walking along the memory banks of the stream... I didn't notice that. That's cute. You find a small village that is experiencing a little confusion. Some programs can't communicate with each other. Programs in this village communicate using a fixed set of pipes. Messages are passed between programs using these pipes, but most programs aren't connected to each other directly. Instead, programs pass messages between each other until the message reaches the intended recipient. For some reason, though, some of those messages aren't ever reaching their intended recipient, and the programs suspect that some pipes are missing. They would like you to investigate. You walk through the village and record the ID of each program and the IDs with which it communicates directly. That's your puzzle input. Each program has one or more programs with which it can communicate, and these pipes are bidirectional. If 8 says it can communicate with 11, then 11 will say it can communicate with 8. You need to figure out how many programs are in the group that contains program ID 0. And so here's what our input likes, and like 0 can talk to 2, and therefore 2 can talk to 0 as well, but then there's others. So how many programs are in the group that contains program ID 0? Well, actually, first let's check out this, and I'll show you just part 1. By the way, did you guys notice Git LGO? You can turn on, and I did this a long time ago, Git has a spelling correction or a typo correction feature, which you may opt into. You can turn on, and you give it a delay, which is like, you can say, oh, please, Git will say, did you mean git log? I think you did mean git log, and in 5 seconds, if you don't say anything, I'll invoke git log for you. But I just turn that delay to 0 and say go right away. Like, really, what are the odds I accidentally typed the wrong git command? And even if I did, like, I know how to fix it, so it's fine. Anyway, so here we are in day 12 source main. Yes. So this was another puzzle where I thought I wanted a state and a map. Pretty useful pair of things to have. Let me tell you some more about... is there a good Wikipedia article on this? Wikipedia union find. Oh, right, it's the disjoint set data structure. Okay. So what we're trying to do, basically, is partition the input in some way, right? We have a set of objects, and we want to find, and we have links between objects, and we want to conglomerate all of the links. So, they have this example here. Here's these 8 things, and like, you find them glued together somehow, and you find these 3 connected subcomponents, basically. And so I remembered that there's like a famous algorithm for doing this quite efficiently called union find. And I always forget the details of like how to do it right. But the idea is that you maintain like a... Sort of the obvious thing is like, oh, you have a set of nodes where like when you find out that 2 things want to be... 2 sets want to be unioned, you don't have to do like a full set union of everything in those 2 sets. You just change like the parent pointer of one of the sets to now point to the other one. So you don't use like a general set. You use a set that's easy to like concat to, basically, but hard to do lookups for. And then you separately maintain like a list of which set each item belongs to. So... Right, so the idea is that you make sets of objects, starting with singleton sets when you don't know about any connections. And to find an element, you look at its parent. And if it has a parent, then like you keep traversing up the tree until you get to the root, and you say, that thing at the root is the characteristic element of this set, the one chosen to nominate the whole set. And a union operation is you give an X and a Y, you find the root of both of those. If they're the same, you're done. If they're different, you change the smaller tree's parent pointer to point to the root of the larger tree. And in this way, it's sort of funny that we're building the tree from the leaves up. So we have leaf pointers to start with, and we trace them back up to their roots rather than the opposite direction. This means we don't have to worry about like keeping the tree balanced or anything. And it's very cheap to concatenate or union two sets together. And there's some optimizations here to do this quickly. In particular, like when you find the parent of a node, you can, when you look up node and you find that it has a parent other than a characteristic root element, when you're done finding the node, you also update its parent pointer to be the root of the tree it happens to be in. And in this way, you typically have a very, very short path from a node to its root, rather than letting that length grow arbitrarily. So that's sort of the basic idea. How did we do it? I defined a few types here. So like a lot of things when you're looking up an algorithm for how to do something, the pseudocode it's written in is often like assuming that mutating things is okay and that like you have objects and they have fields and so on. And so sometimes when you're writing in a functional language, you have to understand how to make those translations, right? Because we can't do that. Like if you look over at the article, it says like in the implementation of find, you're returning X's parent pointer, but you're also mutating X to have its parent pointer be different sometimes, right? We can't easily do that exactly in Haskell, or likewise in Clojure, for example. But you can always simulate this by just adding like an extra level of indirection, basically. For example, instead of having the objects point to a parent struct, we can have the object just have as its value an int, and we look up that int in the tree, and like we're sort of building our own pointer system, and we can update the tree as a separate step without having to also update all the things that point to a thing. And then the other thing is that like having a state monad helps you organize the stuff that you're choosing to pretend is mutable. You sort of opt into this, and it's nice because you can act as though things are mutable, but also be guaranteed that the only things that act that way are the ones you specifically said should be, which is nice. So anyway, we have, I defined a type for a program and said like that's just an integer. And what information do we need to know about a program? We need to know its parent, which is a program. We could have written here maybe program and then had like the parent be, make the root have no parent, for example. But A, that's a little bit more like overhead, not that that performance really matters. B, it would be a difference from the standard algorithm that would just be a little bit harder to remember. And it doesn't really help that much. It's kind of nice to know, in fact, what node is characteristic of this item. And it's easier to track if you just say, oh, it's yourself. And rank, which is sort of the size of the tree that this node belongs to, which is used for more efficient unioning. And so the main, this doesn't need to be in parentheses. The main thing that we're keeping mutably is this thing that I call a directory, a map from each program to its program info. Pretty simple. And finally, a new type, a parameterized type, taking a type A, which is just a stateful computation whose result is of type A, where the state you are tracking is a directory. So we're opting in to say, I want to be able to compute things of any type, while keeping a sort of mutable directory around. So what do? Well, we implement like the functions, there we go, in the Wikipedia article, basically. And so we have this make set, and like each of these are very, I think, straightforward. I'm sorry I can't easily show you guys the two things side by side. Yeah, that sounds hard. But have a look at the find function here, right? It says if x.parent is not x, then change x.parent to be the result of finding x's parent, and finally return x.parent. So this is recursive, of course. And I guess it may not, if you're not super familiar with Haskell, it may not be obvious how this is a very strict translation of that. But it actually is. It's doing precisely the same thing. Modify is a function in the state monad which says make the next argument should be a function, apply that function to the current state, and make that the new state. And our function is m.insertWith. We'll skip this for a second. P is the key that we want to insert at, and the value that we want to insert there is a program info saying that the parent of P is P, and the tree's rank is 0. Now flip const is a function that takes two values and returns the second one. Kind of like pointless, right? But it's nice to pass as an argument to insert with. Insert with says, okay, give me a key and a value, and I'll put the value in the tree under that value, or the map under that value. But if the value is already there, I'll call your function with the old and new value and let you tell me what to do, what to put there. So flip const is a thing saying, okay, we're going to put an empty thing at P unless there's already something there, in which case use the thing that was there. So that's sort of like a put if empty operation that we've built here. So we're modifying the state to contain an empty mapping for P if there wasn't already one. And then gets is a function that says, please pass me a function, and I'll call that function on the state and return to you the value that we got there. And so this is a function that says, please look up in the map that is the state the value P. So make set puts the thing there if it's not there, and then returns what's there. Kind of like, I don't know. This is, I think, not code that I would write if, I mean, I guess it is, right? I was thinking it's not code I would write if I were going to show to a beginner. But I guess that's what I'm doing now, so maybe I'm wrong about that. It's dense, right? It's doing a lot of stuff in relatively few words. Anyway, I think it's sort of elegant. We could have written something a lot like, what else could we do? We could write, okay, set P equals do, M, so call get and store the result in M, where get just tells you what the current state is. If m.member PM, then gets, no, then m dot p else, let's do that picture here, else do m dot insert p pip 0 pure else let, I guess, pi equal this in do this pure, like we could write something like this. Not in scope pure, really? do I have to import control.applicative to get that? Alright, well, we'll use return then. They're the same thing. Sorry, excuse me, where was I? I was looking up, why do I not have pure? I should have pure, because it works in those other things. I must not be in Intero mode, and it's using just plain old Haskell mode, yeah. Now let's put these back. Couldn't match state T. M.insert is applied. There we go. Okay, so we could write this, right? This is sort of a do-based way to do everything in the smallest, most concrete way possible. Tell me the value of this. What is the value of that? Make this change. Return this value. Sort of imperative style. But we have higher order functions to let us do these sort of complicated operations, or not complicated, but many part operations using a slightly richer vocabulary, but fewer words, I suppose. Okay, great. So we have this. I think this is a great way to write make set. And find is a function that takes a program and computes for you a program info, provided, remember what lookup is all about. Lookup says it'll give you what it says over here, a program info, provided that there's a stateful, mutable directory lying around that it can look up. And so find P is basically, well, first we make the set P, which remember is either look it up in the map if it's already there, or else make a new one. And if P's parent is itself, then we found the root. That's it. We just return it. Otherwise, we find P's parent, saving that value to root, and modify the map by changing P's entry to be the entry that we found at root. And then we return the root. Now we could make this like substantially more concise as well, if we wanted. Like for example, if we go and look at the, where's find? Yeah, find. Like this is like relatively few words, right? It's a function that is easier to write in a mutable language, no question about it. Where we have fields and you can just modify them whenever you want. We could write something maybe not exactly as concise, but pretty close. If we were to, let's see. If like this bracket, this area here could be like a bit fancier. You know, what exactly could we do? We could write let's see. I mean, yeah, maybe it's not so clear how to do this, because there's this bind operation here is doing like some relatively cool stuff. It definitely is possible, of course. You could golf this down to one line. There's no reason it has to be multiple operations. But I think that this is pretty clear what we're saying. We look up the parent recursively, of course. Overwrite P to be the same thing as the parent, and then we're done. And finally, union is, it looks a lot like the Wikipedia algorithm. If you look over here at union, we look up the roots of x and y, we check whether they're the same root. And this pseudocode, by the way, is like really bizarre. Like, it doesn't it treats numbers. It treats nodes as if they were like both numbers and objects at the same time, which gave me some trouble in like translating it. Right, because here we're like comparing these things, but here we're setting fields of them. I don't know if they intend these to be like, I guess they intend this to be a pointer equality on a data structure, maybe. So maybe, yeah, I guess. Yeah, they must mean that. Anyway, we check whether they're the same, in which case we don't do anything. If they're not, we find the one of them which is smaller, and make that be make the taller one be the root of the new joined tree. And if they're tied, then we join them together and make one of them bigger than the other. So, and what we do here is very, very similar. We find x and find y, breaking apart the structs that we got back into their two component parts. And we say when they do not have the same root, then compare the rank of the two things. So this is, I don't think you guys have seen compare yet. Compare is a function that takes two values and tells you whether the first one is less than, greater than, or the same as the second. I'm seeing here a few ways that this could be improved. For example, we don't need a do here because it's just one expression. We're just calling like I do need a $ sign though. Okay. We don't need a do because we're not combining multiple multiple statements in a stateful computation. And another kind of cool thing is we can write this, I think. We can get all the modifies out. Yeah. Saves us a little space. So what I was doing was saying, when they're different, then do a thing. And the thing you should do is, depending on comparing these things, and either modify this, or modify that, or modify that. But what we can say is, instead, when they have different roots, modify them in the following way. And the following way will be different depending on how you compare them. But we don't have to repeat the modify over and over, which is nice. If X rank has a smaller rank than Y rank, then we insert Y's node as the value for X's thing, right? So, and if they're the same, then we call union, which I'm basically just using this to insert twice. Insert both this pair and this pair. Pretty simple, I think. I gotta say though, this construct here, when condition composed with modify on blah is like, I don't know, it feels weird to me. Obviously this is also, nope, yeah, that's also correct. I think I like it better this way. Maybe that's because I'm a beginner, but I think it's more, it feels weird to compose when condition with something rather than calling it with something, even though like they're really the same thing. And we needed a parser for our input, which is pretty simple. We'll get to flatten in a minute. The parser just takes like a line, which is a list of words, splits it on the one word that is this kind of spaceship operator thing, and just returns a list of all the programs that were on that line, ignoring which one came first. Which it does by splitting on comma, like blah, blah, blah. Or removing commas, I guess, since we already split on spaces. And the last thing that we have to do is, again, let's leave flatten for a moment. you can write part 1, and it's very nice, and you say, what is the answer for part 1? It's sort of like, well, just look up all the elements of M where it is the case that the parent of the node in the element is equal to the goal. I had first written this, where the parent of the node is 0. But we didn't necessarily choose 0 as the characteristic element for our set containing 0. We kind of have to look up in the tree, hey, what is the root of 0? And then look up all the other nodes that have the same root. And so that's what this is all about. We look up 0 and store its parent. And then we look for all other nodes that have the same parent. And count how many of them there are with length. The trick is, though, this only works if the tree is maximally flattened, where every node points directly to its root. We could have changed part 1 to use the find operation, which automatically, which fixes up parent pointers as it goes. The trick is that the find operation relies on the directory being mutable. And the signature of part 1 that I have written does not permit this. It says, you give me a single directory, and I promise not to change it. And I will look up what's there. And so our find won't work. The types don't match at all. You can't use find anymore if you're not in the context of a lookup. So, in a way, I wrote sort of an inflexible program, and it kind of sucks that you can't use find for that. I could have changed the type, but you have to be a little bit careful there, not to let modifications leak in from like part 1 to part 2 and so on. And so I said, well, we'll just do a final step. Flatten is the function that sets up the stateful context that all the other stuff runs in, and then runs the stateful computation and looks at what the answer was. And so I had flatten just say, basically, what do? We map over all of the neighbors, which is each line of the input, calling process. And process is just take all the keys on the line and call the union function on them. Mapm underscore is a function that takes a list of stateful computations and does them all in order. And it takes care of threading the state value through each of those smaller computations. So anyway, first we process all of those things, and now we have a correct tree where everything knows what its root is. But we do, as a last step, mapm find over all the keys. We just say, look, give me all the keys, and I'm going to call find to fix them all up so they all point directly at the root. It's not necessarily the most elegant thing in the world, but it works. And then part 1 can just look up at the direct parent of each node and be guaranteed that that's always actually its characteristic root value. And of course, main is pretty boring. Okay, great. So first of all, I want to add these changes where we removed an extra parenthesis there. Don't check in that extra new line. Do check in that little cleanup. Git commit -m day 12 style cleanup. Now, what I really should do is, let's see, git checkout master, git, no, there we go. Now git checkout master and git rebase, no, git cherry pick the commit we were just on. There we go. And let's now check out this so I can show you. Man, I really need to get a better solution for mounting the mic, because it has a clip on it that's supposed to clip on the back of your monitor, but the back of my monitor is curved, and so the mic just barely precariously stands on top, and it falls off. It sucks. I don't know exactly what to do about that. I have to keep editing stuff. Also could use a longer wire. Anyway, the point is we don't have to I was gonna like go check out the commit at which we did part 2, but you don't actually have to do that because I've cherry picked the change and checked out ahead. Anyway, I guess even better would be to tell you guys what the heck is part 2, right? Part 2 is basically just asking a slightly different question. How many different groups are there? So we found how many things are in the group rooted at 0, but now they're asking how many distinct roots are there? This is quite straightforward. Actually, let's see. Did I do anything interesting here? No. This is a very nice part 2, I think. I didn't have to change anything about my models or about part 1. I just said, write a new function from directory to int that takes the directory we computed and looks up the parent of each node and nub, which filters basically only the distinct items of that list, and tell me what the length is. So a very nice and easy part 2. I'm always pleased when I can write so straightforward and small a part 2. It means to me that I did a good job of like modeling the problem domain, anticipating what other kinds of questions we might want to answer. And so I sometimes write perhaps a slightly more complicated part 1 than I need to, in anticipation that, hey, who knows what kind of question will be asked in part 2. I want to have a good domain model. And if it turns out to be extra complexity not needed, well, as long as it was a good model, I'm happy with it. Let's see. Are there any, like, interesting lessons in this program? I don't know, like, there's all this monadic machinery and like mapm and like the backwards bind operator, which is just bind, but it takes its arguments in the opposite order, which is like, why did they even put a function in the language that's like, well, we have f that you can call with x and y, but there's also g that if you call it with y and x, it does the same thing. I don't know. I think that it's just to give you the freedom to write in whatever style is the most expressive and clear. Here, I think it's quite nice to say, we're mapping a function monadically over the result of calling gets m keys. We could instead have written gets m.keys bound to mapm find, which is the same exact operation, but sort of emphasizing something different. Emphasizing, I want to do some stuff to the keys of the list, and what I want to do is map find over them. But I think it's often clearer to say, I want to find all of the keys in the list. You know, whatever. Maybe I make a bigger deal of that than is really necessary, but I think it's nice to have both sometimes. And here, like, I don't know, something similar occurs here. This weird $ with brackets operator is the same as map, basically, but as an operator instead of as a function. And it turns out to be nicer in a lot of cases, besides being more general, really. Of course, it's fmap, not just map. We could instead have written parse of this equals map read of something. For example, suppose we tried to do this. This won't parse, or it won't work. Shouldn't work. Why am I not getting an error? That doesn't seem right at all. It's not right. Okay, good. We somehow left in Taro mode again? There we go. Okay, that explains it. Yeah, so this doesn't work at all. Even though, like, this is the same function as map, it has the wrong... Map has the wrong, like, operator associativity. It's like, really what we need is this. Overlapping patterns? Yeah, okay. And, you know, it's not like it's super important that we got 2 characters fewer, but by using an operator which has a convenient and correct associativity and fixity, we don't need these extra parentheses. And we can say read the result of doing all this, or map read over all of this stuff. I don't know. So these are both perfectly reasonable programs. I would not take any issue with someone who wrote this. But it's nice to have both options if you think one of them is more reasonable. Yeah, no changes. Okay. Well, that is it for this episode. For you guys, anyway. I have some editing to do. Gotta glue together those 3 snippets. Blah. Anyway, we're done. See you guys in day 14, I think. Yeah, 14 is next. Thanks for watching, and I'll see you next time.